Hi, this is Arunno, and in this lecture, I am going to discuss the basic things of op-amps or operational amplifiers. Okay, so let's get started. So first, I would like to draw the symbol of an op-amp. This is the symbol of an op-amp. It has two input terminals and one output terminal. One of the input terminals is marked as positive, and the other terminal is marked as negative. And the output voltage can be denoted as V0 or V output, and the input voltages can be denoted as Vi plus and Vi minus. Okay, so what does an op-amp do? It actually amplifies the input voltages. V0 is actually the amplified version of the difference between the input voltages, which is Vi plus minus Vi minus, and it gets amplified, so there will be an amplification factor. In an ideal op-amp, the A is generally infinity. Here, A, which is the amplification factor, it has a particular name. It's called open loop voltage gain. And these two terminals, positive and negative, the positive one is called non-inverting terminal and the negative one is called inverting terminal. But I prefer to call it positive terminal and negative terminal. It's quite easy to remember. The op-amp has power source. Here, positive voltage is given in this terminal, and the terminal in the downside, here negative voltage is given. These two voltages are called bias voltages. This is positive bias, this is negative bias. These two voltages actually work as a power source of this op-amp. These two actually keep the output of the op-amp voltage limited. Imagine the difference between Vi plus and Vi minus is, let's say, 1 millivolt. As we know, the ideal op-amps amplification factor or open loop voltage gain is infinity, but in real op-amps the A is not, infinity, but it's still pretty huge. Let's say it is 100 into 10 cube or 10 to the power 5. So what will be the output? V0 is equal to A into Vi plus minus Vi minus. It will be 1 milli, so 100 volts. But the question is, will we actually get V0 is equal to 100 volt? The answer is no. It depends on the bias voltages. If we give plus 15 volt bias voltage as the positive bias, and in negative bias, let's say we gave minus 15 volt, then we will never get the output voltage more than 15 volt. That is, it actually limits the output from being too large. So if we have got 100 volt as the output voltage in calculation, but in practical we will get only 15 volt because we have given that much bias voltage. If we give bias voltage plus 5 in the positive bias, then we will get the highest voltage output as plus 5 volt. Same thing goes with the negative bias also. If the difference between these two voltages is, let's say, minus 1 millivolt, then our output will be, actually if we calculate it, it becomes 100 volt, but in practice we will get only minus 15 volt because we have given that much amount in the negative bias. So this is the main function, not main, this is also a function of the bias voltages. So now let's discuss about the ideal op-amp characteristics. So the first characteristic of an ideal op-amp is the input voltages of the non-inverting and the inverting terminals will be same or equal. Second important characteristic is the input currents for both inverting and non-inverting terminals will be 0, and the open loop voltage gain, which we mentioned as A, it will be infinity. There are other characteristics also for ideal op-amp, but for now let's stick to these three only. Now let's see some applications of op-amps. One is inverting and non-inverting amplifiers. The second one is differentiator. The third one is integrator. Fourth one is comparator, and many other applications also. In this lecture we will explore the inverting and non-inverting amplifier. Okay, so now let's see how an inverting amplifier works. So this is the basic configuration of an inverting amplifier. Here we can see that the positive terminal is connected to the ground, so Vi plus will be 0. We know that the input voltages of both terminals are same, so Vi minus will also be 0. Okay, so now let's calculate this current I1. I1 is V input minus Vi minus, and it will be divided by R1. This is the basic Ohm's law. I minus is equal to 0, so I1 is equal to V input divided by R1. Similarly, now let's calculate I2. I2 will be Vi minus V0 divided by R2. So putting the value of Vi minus is equal to, it will make I2 minus V0 divided by R2. Now let's recall another characteristic of an op-amp. The input currents are also 0. So in this branch the current will be 0. So I is equal to 0. So now let's consider this node here. Let's denote it node 1. At node 1, if we look at it, we can see that in node 1 there are two output currents. Here I2, here I, and one input current. So if we apply KCL at node 1, the whole equation will be I1 is equal to I2 plus I. As I is equal to 0, so I1 is equal to I2. Now let's put the values of I1 and I2. I1 is V input divided by R1, and I2 is equal to minus V0 by R2. Now V input into R2 divided by R1 is equal to minus V0. So V0 will be minus R2 by R1 into V input. So we can easily notice that V output is amplified by the factor of R2 divided by R1, and there is a minus sign. So the input voltage actually inverted. There is a shift in the sign of the input voltage. So if you put R2 is equal to 2K for an example, and R1 is equal to 1K, then V0 will be minus 2 V input. It will be doubled in the negative way. So yeah, that's how an inverting amplifier works. Okay, so now let's see how a non-inverting amplifier works. This is the circuit configuration of non-inverting amplifier. The positive terminal is connected to a voltage source, and the negative terminal is connected to the ground through a resistance. Now let's calculate this current. Before that, we have to define V pi plus and Vi minus. Vi plus is exactly the V input, so it will be V input, and as we know that the input voltages are same, so Vi minus will also be V input. Now let's calculate I1. I1 is equal to, here this is 0 volt and this is V input, so I1 is 0 minus V in divided by R1. Now let's calculate I2. V input minus V0 divided by R2. And so now look at this node. Let's call it node 1. If we apply KCL to this node, we can see that, as we already know, that this current is 0. So I1 will exactly the same as I2 according to the KCL. So I1 is I2. Now let's put the values of I1 and I2. If we calculate it, so here we are getting that V naught or V output is equal to V in plus V in R2 by R1. So ultimately V naught is equal to 1 plus R2 by R1 into V input. So here we can see that the output voltage is the amplified version of the input voltage, but there is no negative sign. So that's why it is called non-inverting amplifier. If you put R2 is equal to 1K and R1 is equal to 1K, so V0 is then 1 plus 1 into V input, that is 2V in. The output voltage is doubled if you use R2 1K. Now this R2 is called actually the feedback resistance or RF. It is also true for the inverting amplifier. So that's how a non-inverting amplifier works.